We all grow up hearing one simple sentence: gravity pulls things down. An apple falls, a pen drops, we stay on the ground, end of story. But pause for a second. If gravity is just a force pulling downward, why do astronauts float inside the space station, even though they are still inside Earth's gravity? If gravity always pulls things in, why doesn't the moon fall straight into the Earth? And why did Richard Feynman, one of the greatest physicists who ever lived, quietly admit that we don't really understand gravity the way we think we do? How can something so familiar, something that shapes every moment of our lives, be so deeply misunderstood? By the end of this video, gravity will feel less obvious and far more beautiful. Think back to the first time you learned about gravity in school. The teacher probably said something like this: gravity is a force. The Earth pulls objects toward itself. That's why things fall. It sounds clean, logical, almost too simple. In our heads, gravity becomes like a magnet, invisible, steady, pulling everything inward. Drop a ball and the Earth reaches out and grabs it. And for everyday life, this explanation works well enough. You jump, you come back down. You let go of your phone, it doesn't float, it falls. So we stop questioning it. But here's the strange part. This picture of gravity as a pulling force is not actually wrong. It's just not the full story. Imagine a magnet again, pulling iron filings across a table. You can almost see the force acting, dragging the pieces closer. Now try to imagine gravity doing the same thing. Where is the pull coming from? What is it reaching through? Physicists notice something uncomfortable here. Unlike other forces, gravity doesn't behave like a clear push or pull. There's no obvious handle it grabs onto. It doesn't weaken the same way. And most strangely, everything falls the same way, no matter what it's made of. That should bother us more than it does. Because when we say gravity pulls things down, we're really using a shortcut, a convenient story our brains can handle. A story that hides deeper questions instead of answering them. And this is the quiet truth most textbooks never say out loud. Gravity as a simple force explains what happens, but not why it happens that way. Once you notice that gap, you can't unsee it. And in the next part of our story, that gap leads to an even stranger realization, that falling might not be what we think it is at all. Right now, as you're watching this, you probably feel perfectly still. You feel your weight, your feet on the floor, your body calmly at rest. It feels normal, almost invisible. Now imagine this instead. You step into an elevator, the doors close, and suddenly, the cable snaps. For a brief moment, everything inside floats. Your stomach rises. The floor no longer feels solid. Panic kicks in instantly. Here's the strange part. Gravity did not suddenly turn off. Earth didn't stop pulling you. The laws of physics didn't break. So why did everything feel so wrong? Because what you normally feel is not gravity pulling you down. What you feel is the floor pushing you up. That idea sounds backwards at first, but sit with it. When you're standing still, gravity is trying to make you fall. But the ground refuses to let you. It pushes back on your feet, your bones, your muscles. That push is what your body interprets as weight. The moment the elevator starts falling, that push disappears. Nothing is supporting you anymore. And suddenly you feel weightless. Not because gravity is gone, but because resistance is gone. This is why astronauts float inside the space station. They're not beyond gravity. Earth is pulling on them constantly. But they, the station, and everything inside it are all falling together. No floor pushing back, no resistance. And here's a powerful truth hiding in plain sight. Free fall is the most natural motion under gravity. Standing still is what's unnatural. Once you realize that, gravity stops feeling like a force attacking you and starts feeling like something far stranger. In the next part, we'll meet a physicist who was deeply uncomfortable with this idea and honest enough to admit how little we truly understand it. Richard Feynman was not the kind of scientist who liked pretending. He helped explain how atoms behave. He reshaped quantum physics. He could take the most complex ideas in science and make them feel almost obvious. And yet, when it came to gravity, Feynman sounded uncomfortable. He once said, very plainly, that we don't really understand gravity, not in the deep physical sense we think we do. At first, that sounds impossible. We can calculate planetary orbits centuries into the future. We can land spacecraft on distant worlds. We can predict eclipses down to the second. So what was missing? Feynman pointed out something subtle. Physics often gives us equations that work, but working equations are not the same as real understanding. Think about driving a car. You know exactly how to press the accelerator. You know how hard to turn the wheel. You can drive across an entire country without a problem. But if someone asked you to explain what's happening inside the engine, how fuel becomes motion, how metal parts coordinate perfectly at thousands of explosions per minute, most of us would fall silent. That's how gravity looks to physicists. We know how to use it. We know how to calculate it. But when we ask the deeper question, what is gravity actually doing? The answers suddenly become vague. Feynman didn't see this as a failure. He saw it as honesty. Admitting confusion wasn't weakness to him. It was the starting point of real discovery. And here's the quiet realization hiding in his words. Knowing the math of gravity is not the same as knowing its nature. That discomfort, that gap in understanding, is what pushed physicists toward an idea that would completely change how we see space itself. And that's where our story goes next. For a long time, gravity was treated like an invisible hand, something reaching across empty space and pulling objects together. Then Einstein came along and quietly asked a different question. What if space itself is not empty? What if it can bend? This idea sounds abstract, so let's slow it down and picture it. Imagine a stretched rubber sheet. Now place a heavy ball in the center. The sheet dips, curves, reshapes itself. If you roll a smaller ball nearby, it doesn't need to be pulled. It simply follows the curve. To the small ball, it feels like a force. But from above, you can see the truth. It's just moving along a warped surface. Einstein said gravity works the same way. Earth doesn't reach out and pull the moon. The sun doesn't grab the planets. Mass bends space and time around it, and objects move along the paths that curved space allows. This is why astronauts float. They're not escaping gravity. They're moving freely through curved space-time, following the straightest possible path in a bent universe. Once you accept this, reality feels different. Space is no longer a silent stage where things happen. It becomes an active participant. It stretches. It curves. It tells matter how to move. And here's the beautiful shift in perspective. Objects don't fall because they're pulled. They fall because space itself is telling them where to go. This idea didn't just sound elegant. It made predictions that could be tested about light bending, time slowing, and orbits behaving in strange ways. And in the next part, we'll see how this bending of space explains something we see every night in the sky. The moon endlessly falling and never crashing. Look up at the moon on any clear night. It feels calm, stable, as if it's been placed there, perfectly balanced forever. But that calmness is an illusion. The moon is not hovering. It is not held in place by some delicate cosmic balance. The moon is falling. Imagine standing on a high mountain with a stone in your hand. You throw it forward. It travels a little, and then falls to the ground. Now throw it harder. It goes farther before it falls. Harder still, farther again. Now here's the leap of imagination. Throw it so fast that as it falls, the earth curves away beneath it. The stone never hits the ground. It keeps falling and missing. That is an orbit. The moon is constantly falling toward Earth, but it has so much sideways motion that it keeps missing the planet beneath it. No force is holding it up. No invisible hand is supporting it. It is simply following the curved shape of space around Earth. This is what Einstein's picture makes clear. Orbits are not balance. They are motion. And once you see it this way, the universe feels strangely elegant. The same rule that makes an apple fall also keeps the moon in the sky. Here's the quiet beauty of it. An orbit is just a beautiful way of missing the ground forever. In the next part, this idea of curved space will stretch even further, because it doesn't just guide motion. It quietly changes time itself. At first, the idea sounds like science fiction. Gravity bends space, fine. But time? It feels too strange to be real. So imagine something simple. Two identical clocks, one placed at sea level, the other carried to the top of a mountain. They start perfectly synchronized. Now wait. Very slowly, silently, something unexpected happens. The clock on the mountain begins to run a little faster than the one below. Not because it's broken. Not because of temperature or mechanics. But because gravity is weaker higher up. Einstein predicted this. And unlike many strange ideas in physics, this one didn't stay theoretical. We measured it. Atomic clocks are so precise that they can detect this tiny difference. Time itself flows at slightly different rates depending on how deep you are in gravity. This isn't a metaphor. It's not philosophical. It's practical. Your phone's GPS works only because engineers correct for gravitational time distortion. Satellites experience weaker gravity than we do, so their clocks tick faster. If we ignored this effect, your location would drift by kilometers every single day. And here's the quiet realization that changes how time feels. There is no single universal now. Every clock carries its own rhythm, shaped by motion and gravity. The deeper you go into gravity, the slower time moves. So gravity doesn't just decide where things fall, it decides how fast moments pass. And once time itself becomes flexible, we're forced to confront an even bigger mystery. Because gravity, for all its power, still refuses to fit neatly into our deepest theories. That's where we're going next. By now, gravity may feel more elegant than mysterious. It bends space. It shapes time. It guides planets, light, and even your phone's GPS. And yet, here's the strange truth. Gravity does not fit. Modern physics rests on two incredibly successful ideas. One explains the very large, planets, stars, galaxies, space-time itself. The other explains the very small, atoms, particles, the quantum world. Each theory works perfectly in its own domain. But when we try to place them on top of each other, like two detailed maps of the same city, the streets don't line up. Gravity refuses to behave like the other forces at the quantum level. It doesn't break into clean particles the way we expect. The math starts to misbehave. Predictions lose meaning. And this isn't a minor technical issue. It shows up at the most extreme places in the universe. Inside black holes, at the beginning of time, where space-time itself becomes unstable. This is why physicists say gravity is unfinished. Not because it fails, but because it works too well in one language and refuses to speak the other. Richard Feynman was deeply aware of this gap. He knew that understanding gravity wasn't about finding better equations alone. It was about discovering a deeper description of reality itself. And here's the most honest thing we can say. Gravity works flawlessly, even while hiding its true nature. That mystery is not a flaw in science. It's an invitation. Because the universe has not finished telling us its story, and gravity may be the sentence we're still learning how to read. When we started, gravity felt obvious. Things fall. We stay grounded, end of explanation. But along the way, something shifted. We saw that falling is not failure, it's freedom. That weight is not gravity pulling, it's the ground pushing back. That space is not empty, it bends. That the moon survives by endlessly falling and missing. That time itself slows under gravity's touch. And that even today, gravity refuses to fully reveal what it is. What began as a simple force turned into a story about reality itself. Gravity isn't just something acting inside the universe. It is part of the universe's structure. It tells matter how to move, and tells time how to flow. And maybe that's why Richard Feynman was uneasy. Because the closer we look at gravity, the more it stops feeling like a thing, and starts feeling like a clue. A clue that space, time, motion, and existence are far more connected than our intuition ever suggested. So here's the thought to sit with. If gravity is not a force pulling objects, but the shape of reality guiding them, then what does that say about the rest of the universe? That still feels solid, fixed, and obvious to us? I'll leave you with that question.